Signals and Systems Classification Series on Signals and Systems, Lecture number 1.13. Signal is a vehicle. Signal is a carriage. Signal is used to transport information from one point to another point in communication systems. In the present session, our focus is on various classifications of signals. Before going to the classifications, we spend some time on the definition of a signal. Signal is a waveform or a function of one or more variables which conveys information on the nature of a physical phenomena. The important aspect to be noted from this definition is that signal refers to a waveform that is capable of carrying information. Only those waveforms which can hold information, which can carry information, which can transport information, they are only signals. If the waveform is of current or voltage, then it is called electrical signal. Signal can be a mechanical one too. An example for mechanical signal is sound. If the waveform is of current or voltage or field, it may be electric field or it may be magnetic field. In all these cases, the signal is called electrical signal. Some more information regarding the nature of signal. When the signal or function depends upon a single variable, then it is called one-dimensional. Speech is an example for one-dimensional signal. Of course, it is mechanical signal, one-dimensional mechanical signal. If the function or signal depends upon two or more variables, then the signal is said to be multi-dimensional. More than one independent variables are there, then it is multi-dimensional. Some examples to multi-dimensional signals are given here. Static pictures. These are examples for two-dimensional signals. Motion pictures. These are examples for three-dimensional signals. Temperature, wind speed, air pressure, etc. At a point in space. These are examples for four-dimensional signals. In case of static pictures, independent variables are two, horizontal position and vertical position, and hence they are two-dimensional signals. In case of motion pictures, independent variables are three, horizontal position, vertical position plus time. Hence, they belong to three-dimensional signals. Temperature, wind speed, air pressure. They vary from point to point in space. Space is a three-dimensional entity. And these quantities vary with time too. Therefore, another dimension, time, comes into picture. So they are examples for four-dimensional signals. Now we move on to classifications. Several classifications are there. One after another we consider. First we consider signal classification into CT and DT signals. CT stands for continuous time, DT stands for discrete time. A signal is said to be a CT signal, continuous time signal, if it is defined for all values of the time t. CT signals arise naturally when a physical waveform such as acoustic wave, sound wave, mechanical wave, or light wave is converted into an electrical form, into an electrical signal. DT signal, discrete time signal, is one which is defined only at discrete instants of time n, small n. This is called time index and it assumes only integer values. This signal is also called a time sequence. DT signal is also called time sequence because it consists of a sequence of numbers. One can notice from the definitions the basic difference between CT signal and DT signal is CT signal is defined for all instants of time, whereas DT is defined only for specific or particular instants of time. Some more information on CT and DT signals. A DT signal can be derived by sampling a CT signal at a uniform rate. X of n is equal to x of nts, where ts is sampling period. The basic point from this statement to be noted is that DT signal is related to CT signal. The connection between them is through a process called sampling. By sampling a CT signal, a DT signal comes into being. Some information regarding representation of signals. A DT signal can be represented in one of four forms. What are those four forms? Graphical representation. Graphical means in the form of a picture. Functional representation, that is in the form of a mathematical expression. Tabular representation in the form of a table. Sequence representation. These are four forms. One can specify a DT signal in any one of these four following forms according to the convenience. Similarly, a CT signal, it can be represented in different forms. Here it is two. One is graphical representation, another is functional representation. Graphical means in the form of a picture. Functional means in the form of a mathematical or analytical expression. Another classification is into analog and digital signals. Analog signal is related to CT signal. Digital signal is related to DT signal. What is the relation between them? Analog signal is a CT signal x of t, which can take any value in the continuous interval a b, where a can be infinity and b can be minus infinity. It means a CT signal becomes analog signal if it can assume any value ranging from minus infinity to plus infinity. Now, the connection between digital signal and DT signal. Digital signal is a DT signal x of n, which can assume a finite set of distinct values. They can be derived by sampling or discretization in time and quantization in amplitude of CT signals. So here this statement or second sentence of the second bullet point, it says, it gives some information regarding digital signal and CT signal connection. Another classification is into deterministic and random signals. Deterministic signals are those whose values can be specified definitely, not probabilistically at any given time, and these signals are modeled by a known function of time. Now, random signals, what are they? Those that take random values at any given time and are characterized statistically. So probability theory plays an important role in the analysis of random signals. Another classification of signals is into causal and non-causal. What is causal and non-causal signal classification? A CT signal x of t is said to be causal. Note, it is not casual, it is causal if x of t is 0 for t less than 0. Otherwise, the signal is non-causal. For an anti-causal signal, x of t is 0 for t more than 0. So here two terms are there, causal, non-causal, anti-causal. These three terms are to be differentiated. Their difference is required to be keenly noted, observed. If a DT signal x of n, a DT signal x of n is said to be causal if x of n is 0 for n less than 0. Otherwise, the signal is non-causal. For an anti-causal signal, x of n is 0 for n more than 0. Actually, this point is DT version of the point given just now, earlier to this point. Another classification is into real and complex valued signals. A signal is real if it is real valued and it is complex if its value is a complex number. Another classification is into even and odd signals. A CT signal x of t is referred to as an even signal if x of minus t is equal to x of t. Similarly, a DT signal x of n is referred to as an even signal if x of minus n is x of n. So this is the defining statement of an even signal. Then what is odd signal? A CT signal x of t is referred to as an odd signal if x of minus t is minus x of t. A DT signal x of n is referred to as an odd signal if x of minus n is minus of x of n. Even and odd parts of a signal can be separated out using the following relations. If you want even part, one can use this relation. If you want odd part, second one. Xe of t is equal to half x of t plus x of minus t. X of O of t is half x of t minus x of minus t. Similar is the case with the discrete time signals. Any signal x of t, x of n can be expressed as sum of two signals, one odd and one even. Another important aspect is product of two even or odd signals is always even. Two even signals multiplied gives you even. Same is the case with the two odd signals. But the product is odd if one signal is even and the other is odd. Another classification is into periodic and non-periodic signals. A CT signal is said to be periodic with period t if there is a positive non-zero value for t for which x of t plus t is equal to x of t for all t. The fundamental period t naught of the signal x of t is smallest positive value of t satisfying the relation. This is as far as CT signal is concerned. Now we consider the case of DT signal. A DT signal is said to be periodic with the period n, capital N, if there is a positive integer capital N for which x n plus n is equal to x of n for all n. The smallest positive integer capital N satisfying the above relation is the fundamental time period, usually indicated by n naught of the signal x of n. Before going further, one important aspect one has to keep in mind regarding periodic signals is that they start at minus infinity and they extend up to positive infinity. So they are eternal signals. So all periodic signals are eternal, started at minus infinity and they continue up to infinity. Some more information regarding periodic and non-periodic classification. A CT signal or DT sequence, when not periodic or non-periodic or aperiodic. The sum of two periodic DT sequences is always periodic, but sum of two periodic CT signals need not be so. An important aspect one has to keep in mind. For the sum to be periodic, the ratio of the time periods t1 by t2 must be a rational number or ratio of two integers. A sequence obtained by uniform sampling a periodic CT signal need not be periodic. The sampling a periodic signal results in a DT sequence, but it need not be periodic just because its mother CT signal is periodic. A CT sinusoidal signal sin omega naught t is periodic for every omega naught, but DT sinusoidal need not be so. In fact, a DT sinusoidal sequence sin omega naught and t with a sampling period of t is periodic only when omega naught t is a rational number, multiple of pi with period n equal to 2k pi by omega naught t. So differences are there between periodic CT signals and periodic DT signals. Another classification is into energy signals and power signals. A signal is an energy signal if its total energy E is finite. That is, if it satisfies the condition 0 less than E less than infinity. So E energy must be finite. A signal is a power signal if its average power P is finite. That is, satisfies the condition 0 less than p less than infinity. That is, p must be finite. Energy, by definition, actually it is normalized energy of the signal. It is by definition limit t tends to infinity integral t x square t dt. Here xt is the signal. In case of non-periodic signals, it becomes minus infinity to plus infinity x square of t dt. The average power P by definition is limit t tends to infinity 1 by t integral over t x square of t dt. For periodic signals, it becomes 1 by t integration over t x square of t dt. A few important aspects of energy signals and power signals. Their differentiating features, they are mentioned here. Energy signals, power signals. Total normalized energy is finite and non-zero. In case of energy signals, the normalized average power is finite and non-zero in case of power signals. The energy can be obtained using E equal to limit t tends to infinity integration over t x of t whole square dt. It becomes, for non-periodic signals, integral minus infinity to plus infinity modulus or absolute value of x of t whole square. The power is P equal to limit t tends to infinity 1 by t integration over t absolute value of x of t whole square dt. For periodic signals, it becomes 1 by t integral t absolute x of t whole square dt. Non-periodic signals are energy signals, whereas practical periodic signals are power signals. Notice, energy signals are time limited, power signals exist over an infinite time. Power of the energy signal is zero, energy of power signal is infinite. Example for energy signal is a single rectangular pulse. Example for power signal is periodic pulse train. So far, we considered a definition of a signal and then a brief explanation of the definition along with examples, and then several classifications that exist for signals in communication systems. All these aspects are discussed, explained. Hope this session is quite useful to you. We meet again in another session soon with a new topic.